Welcome to the next session, my dear friends. So in the previous session we are discussing about the screening part, and now we are entering into the next topic of our treatment of water, that is sedimentation. So first we are going to discuss plain sedimentation, and then we are going to discuss sedimentation aided with coagulation. So, sedimentation. Sedimentation means the process of removing particles using gravimetric technique. Sedimentation means the process of removing particles, the process of removing particles using gravimetric techniques. Using gravimetric technique and allow the particle to settle upon its own weight. Okay, to allow particle settle on its own weight. That is nothing but sedimentation. There are different types of sedimentations. I already told you. There are basically classification of sedimentation tank can be done in different types. First one is based on external aid. So types of sedimentation tank. So first one is based on external aid. So if you are helping it from the external source, then it is sedimentation aided with the coagulation. If you are no aid, no help is given to the sedimentation tank from externally, that is called plain sedimentation. No external aid. So sedimentation aided with coagulation. So here this is aided coagulation. We add coagulant externally. Okay. So next is based on type of flow. Quiescent type, and second one is continuous type. Quiescent type is also called intermittent See, quiescent means on and off. On and off means we will send water into quiescent type sedimentation tank and we will keep the water at rest for 24 hours time, and then we will take the water out. Whereas continuous type is not like that. The water is continuously flowing. There is no rest to the water. It continuously flows in the sedimentation tank. During the flowing pattern only, during the process of flow, the sedimentation takes place parallelly. Whereas in quiescent type, we will bring the water to rest and we will allow the sedimentation to happen, and then we will draw the water outside the quiescent tank. Okay, that is quiescent type or intermittent type. So quiescent type means fill and draw, fill and draw. So flow is brought to rest here. Flow is brought to rest. So whereas here it is continuous, flow is continuous. So this is also called fill and draw type. Fill and draw. Fill and draw type of sedimentation tank. Okay. Now, next is continuous type of sedimentation tank. Because see, quiescent type is not used these days. This is obsolete these days. It is obsolete. Okay, we are not using quiescent type these days. We are using continuous type only. So continuous type, further there are two types of continuous type. Further there are two types of continuous type of sedimentation tank. Continuous type of sedimentation tank. So continuous type. So it is again two types. One is, so the classification based on the shape of the tank, based on shape of the tank, based on shape of the tank, and based on type of flow, based on type of flow. Based on the shape of the tank, rectangular tank and circular tank. Rectangular tank and circular tank. So for continuous flow type sedimentation tank, there are two types of tanks based on shape, that is rectangular and circular, and two types of flow, that is horizontal flow, horizontal flow preferred for rectangle tank, preferred for rectangle tank, and vertical flow, vertical flow used in circular tank. So based on flow it is vertical and horizontal, based on the shape it is rectangular and circular. Okay, so these are the classification of the sedimentation tanks. Now, so generally quiescent type sedimentation tank, let us discuss a small thing about the quiescent type, and then we will go to the continuous type, because quiescent type we are not using these days, but anyways we will discuss one or two points on QCN type, and then we will move on to the continuous type of sedimentation tank. Okay, now QCN type. See, this QCN type, generally the detention time of this QCN type varies from, DT is called detention time. Detention time varies from 8 to 12 hours. 8 hours to 12 hours. Sorry, 24 hours. Detention time is 24 hours. Detention time is 24 hours. And cleaning period. So generally in QCN type, we will bring the water to rest for 24 hours. That means the detention time is 24 hours. Okay. The detention time is 24 hours. So cleaning period is 8 to 12 hours. For every 8 to 12 hours, we need to clean the tank. For every 8 to 12 hours, we need to clean the tank. Okay. Now that is why, see, a minimum number of 3 are needed. So minimum number of tanks needed. Minimum number of tanks needed is equal to 3 number. Because for every 8 hours, 1 will go to maintenance. That means we need at least 3 to serve 24 hours. Okay. So that means we know number of tanks needed is 3. And the design discharge is maximum daily flow. Maximum daily discharge, that is 1 point times of Q. So maximum daily discharge, for maximum daily discharge, we design this QCN type of sedimentation tank. So this is enough about the QCN type. So let us discuss elaborately about the continuous type sedimentation tank, which is important for GATE examination. Continuous flow sedimentation tank. Sedimentation tank or settling tank. Okay. See here, before going into this analysis of continuous flow settling tank, we have to keep some assumptions. We have to learn some assumptions in it. So what are the assumptions? In the continuous flow type sedimentation tank? Let us see. The first assumption is concentration of suspended particles of each size is same at all points of vertical cross section at the inlet. Concentration of particles of each size, concentration of suspended particles of each size is same at all points of vertical cross section, at all points of vertical cross section at the inlet. So that means when this is a sedimentation tank, okay, so at this is inlet zone here. So this is nothing but the inlet zone. So at this inlet zone, at this vertical cross section, vertical cross section means what? This one. So this is vertical cross. At this vertical cross section, the concentration of suspended particles of each size is same at all the points. See, if you take this vertical cross section, so here the concentration of the particles are same. If you take a vertical cross section here the particles are same. So every vertical cross section, the concentration of the particles are same. That means we assume that the suspended particles are uniformly distributed at the inlet. Okay, that is what is our assumption. Concentration of suspended particle is uniformly distributed at the inlet. That is what is the first assumption. So next assumption is a particle is assumed to be removed. A particle is assumed to be removed only if it reaches to the bottom of the settling zone. A particle is assumed to be removed only when it reaches to the bottom of settling tank, to the bottom of settling zone. To the bottom of settling zone. See, so, here what happens, what is this is, for example, this is a tank. So in a tank there will be two compartments. One is settling zone. This is settling zone. And this one is sludge zone. So when particle is started from here, three particles are started from here. So one particle is reached here. Another particle is reached here. Another particle reached here. So let this particle is A, let this particle is B, let the particle is C. So this particle has reached the bottom of the settling zone. This particle is also reached the bottom of the settling zone, but this particle has not reached the bottom of the settling zone. So only we consider that B and C are removed, A is not removed. Though the A is settled here, we assume that, so whatever the water moving up, so this water will take this particle out. Only when it reaches the bottom of the settling zone, then only we consider that the particle is removed. If it is somewhere other than the bottom of the settling zone, then we don't consider that the particle is removed. That is our second assumption. Okay. So particle is assumed to be removed only when it reaches the bottom of the settling zone. Okay. That is second assumption. Now these are the two assumptions we generally consider for the analysis and design of the sedimentation tank, rectangular type sedimentation tank. Okay. Now, so let us analyze the rectangular type sedimentation tank. Analysis of continuous flow, analysis of rectangular continuous flow type sedimentation tank. Okay. Already we are in continuous flow, that is I have no need to explain it again. Analysis of rectangular tank which is having continuous flow. See here, this is, let us take a tank. So this is a rectangular tank. Here this is the height of the tank or depth of the tank, whatever it may be. So this is the width of the tank and this is the length of the tank. Okay. If we take a particle, if we take any particle anywhere inside, I have taken a small particle here. On this particle, there will be one velocity which is acting downwards. There will be one velocity which is acting horizontally. Vertically, one velocity will act. Horizontally, one velocity will act. The vertical velocity which is acting downward is called Vs. And the velocity which is acting horizontally is called Vh or Vf. Vh or Vf. So, what is Vh? What is Vh or Vf? Vh or Vf is nothing but horizontal velocity or flow velocity. Flow velocity. I told you here the flow is continuously flowing in the tank. The flow is continuously flowing in the tank. So that means the flow will have some velocity, that is nothing but flow velocity. So Vs is settling velocity. Vs is settling velocity. Vs is settling velocity. For example, a particle entered into the tank at the entry position and went out of the tank at the exit position. The particle has to travel a length of L in order to cover the path of the sedimentation tank. Okay, the particle has to cover a length of L in order to cover the path of the sedimentation tank. So from entry to the exit of a particle, it has to travel a length of L. So the time of flow, so Tf is called time of flow. Time of flow. So time of flow is nothing but the time needed for a particle to travel the sedimentation tank along the length direction. To travel the sedimentation tank along the length direction, that is time of flow, which is equal to S is equal to Vt. So we know the length L by Vf is nothing but Tf. Time of flow is nothing but L by length of the tank by velocity of the flow. Okay. Similarly, there will be time for settling also. Time of settling. There will be time for settling also. See, time for settling means the particle is moving in this direction now. It has to cover a distance of height h. So, what is the time needed for a particle at the inlet to travel a distance of h is nothing but time of settling. So, Ts is equal to h by Vs. H by Vs. So, when a particle enters into the sedimentation tank, two velocities are acting on it. One is the flow velocity, one is the settling velocity because of its weight. Now, the particle has, it needs Tf time, that means Tf time to cover the path along the length. It needs Ts time to cover the path along the depth. So, if Tf is more than Ts, okay, if Tf is more than Ts, then the particle reaches first the bottom, then reaching the exit. I am repeating, listen carefully. When Tf is greater than Ts, when Tf is greater than Ts, then particle reaches bottom prior to exit. That means, so when the TF, time of flow, is more, so the particle is slowly traveling in the time of flow horizontal direction, but it is fastly moving in down direction, vertical downward direction. So what happens? So before it covers a TF, TS is completed. So that somewhere here it has settled down. Are you getting me? So when TF is greater than TS, then the particle reaches bottom position first, then exit. If TS is greater than TF, that means here TF is greater than TS means particle is removed. We can also say that the particle is removed in sedimentation tank. Particle is removed. Particle is removed. If TS is greater than TF, so before settling, particle is reaching the exit point. Before settling, the particle is reaching the exit point, then it will escape. So before the settlement time is covered, particle is reaching the exit point, so it can easily escape. So if this is the case, then particle escapes. Then particle escapes. Then particle escapes. So that means the particle will settle inside the sedimentation tank only when the time of flow is greater than or equal to. When the time of flow is greater than or equal to the time of settling. The time of settling. Okay. Now, here, what is the velocity of flow? What is velocity of flow? The velocity of flow is nothing but so discharge is going from the sedimentation tank in this direction. Okay, let Q is the discharge which is going out of the sedimentation tank. Let Q is the discharge. Okay, let Q is the discharge passing through sedimentation tank. Passing through sedimentation tank. Passing through sedimentation tank. Okay. So then Vf is equal to Q upon area. Which area I need to take? See, whenever we take this velocity is in this direction, right? The corresponding perpendicular area. See, if this is the inlet location, this is the velocity of flow. This is the direction of velocity of flow. So then this thing we need to take. What is this thing? So this is width. So velocity of flow is coming like this. This is velocity of flow direction. So this is width of the tank and this is the depth of the tank. So B into H we need to take in order to find the velocity of flow. So B into H. So this is velocity of flow. This is called velocity of flow. So to find the time of flow, we need velocity of flow. Velocity flow we can determine using this thing also, Q by BH. So now, as I told you, the particle will settle only when this time of flow is greater than or equal to time of settling. So when the time of flow is equal to time of settling, okay, this is the worst condition where the particle will settle. This is the worst condition. That means when TF is equal to TS is the worst condition. If TF is greater than TS, then particle will settle 100%. TF is equal to TS is the boundary condition. So when the TF is equal to TS and slightly TS increases, then particle escapes. So the boundary condition for a settlement is TF is equal to TS. The boundary condition, okay? That is the boundary condition. So let us take that boundary condition to analyze the efficiency. and also to analyze the overflow velocity. What is the overflow velocity and all we will discuss. So, if Tf is equal to Ts, then the particle will settle. So, this is the boundary condition. The boundary condition. Just if you shift, if you increase Ts, particle will escape. Slightly if you increase the Tf, particle will settle in advance. Okay, particle will settle in advance. We will understand everything. We will understand. So why this is boundary condition? Now you know why it is boundary condition. So if anything moving up and down, that changes the efficiency. Okay, so at this point the particle will completely settle. Okay, that particle will completely settle. So that is, if Tf is equal to Ts, that means what is Ts now? Ts is equal to Tf means Ts is equal to Q by L by Vf. So as Tf is equal to Ts, that means this is Tf. This is Tf. So Ts is equal to L by Tf, L by Vf, and this Vf is equal to Q by Bh. Right? So this Vf is equal to Q by Bh. So Ts is equal to H by Vs, right? H by Vs, which is equal to L by Lbh by Q. So Vs is equal to, now H gets cancelled. Vs is equal to Q by Bl. This is Q by Bl. This is settling velocity. Actually, this is settling velocity. But this value of Vs, this value, whatever the value of Vs we derive at this boundary condition, whatever the value of settling velocity we derive at this boundary condition, we call this as overflow velocity. Okay, the settling velocity derived at the boundary condition that is Tf is equal to Ts is called overflow velocity or overflow rate. So overflow velocity. So that means we indicate it with V0. So at this condition only, I am repeating it again and again. At this condition, whatever the settling velocity you are defining is called overflow velocity. Overflow velocity is equal to Q by Bl. Settling velocity, why settling velocity is not a constant value? Settling velocity varies from particle to particle. From particle to particle, the settling velocity varies. See, generally, settling velocity is a property of particle. Settling velocity is a property of particle. Whereas overflow velocity is a property of sedimentation tank. Is a property of sedimentation tank. See, for a particular sedimentation tank, here we are nowhere using the properties of particles. Here nowhere we are using the properties of particles. We are using the discharge rate, dimensions of the sedimentation tank. So this is the overflow rate is a property of a sedimentation tank, whereas Vs, here this Vs is different. So the settling velocity actually we calculate from the particle point of view. So the settling velocity we calculate from the particle point of view. That we will learn what is settling velocity exactly, because both are settling velocities only. This is the settling velocity from the point of view of sedimentation tank, and Vs, actually the Vs is the settling velocity from the point of view of the particle. That we will understand, just wait for a while. So this V naught is having different names. In examination, this V naught will be given with different names. Let us see what are the different names that are possible to be given for V naught. Surface loading rate, surface overflow rate. So V naught is called, so V naught is having different names. Surface loading rate, surface overflow rate, surface overflow rate, hydraulic loading rate, hydraulic loading rate, simply overflow velocity. Here I have already told overflow velocity. Okay, these are the different names of the V naught. So the settling velocity needed for, so here this V naught is also called the settling velocity. The settling velocity, or else we can say the minimum settling velocity. Minimum settling velocity needed, the minimum settling velocity needed for 100% removal of particles. 100% removal of particles. For 100% removal of particles, this is the minimum settling velocity needed for 100% removal of the particle. That is nothing but overflow velocity. That is nothing but the overflow velocity. Okay. So then efficiency. What is meant by efficiency? What is meant by efficiency of a sedimentation tank? What is meant by efficiency of a sedimentation tank? The efficiency of a sedimentation tank, let us see. See here, if you take a sedimentation tank, okay, if you take a sedimentation tank, so a particle, one particle is larger, one particle is smaller, one particle is very small, so this is very trace. So here this particle will have a velocity of settling which is Vs1. This particle is having Vs2. This particle is having Vs3. This particle is having Vs4. But this sedimentation tank is having same overflow velocity, that is V0. It is V0. So the sedimentation tank will have same overflow rate, that is V0. So for some particles this Vs1 may be more than V0. For some particles this Vs is equal to V0. For some particles it may be lesser also. So this is V0 is the property of sedimentation tank. If the particle's settling velocity Vs, if the particle settling velocity Vs, if it is greater than V0 or equal to V0, then it will 100% all the particles will settle down. If this Vs is less than V0, then full 100% particle removal may not be possible. 100% particle removal may not be possible. Some 30%, 40% particles may get removed, but rest of the particles will escape. So that is why the efficiency of a sedimentation tank, efficiency of sedimentation tank is defined as N is equal to Vs by V0 into 100. Vs by V0 into 100. Okay. So Vs is the settling velocity of various particles. Vs is the settling velocity of various particles. If Vs is greater than V0, then efficiency is restricted to 100%. That means it should not be more than 100%. The maximum value is 100% only. If Vs is greater than V0, then the efficiency is restricted to 100% only. 100% only. Restricted to 100% only. So when the settling velocity is more, that means when the particle size is larger, see this settling velocity may be more than the overflow velocity of the sedimentation tank. It does not mean that its efficiency is more than 100%, but it will settle down early. It will settle down early. That is the only thing that happens. But it is not that the efficiency is more than 100%. So here we know the formula for V0. So Q by BL is the V0 formula. Then what is the formula for Vs? What is the formula for Vs? So Vs, generally we determine the Vs using the Stokes law concept, that is concept of terminal velocity. So how to determine the Vs and how to determine the efficiency and all we will discuss in the next class. Okay, thank you.